Okay, so problem number 2, a composite of a magnetic circuit. Yes, I'm host now. Yeah. Okay. I was thinking that we can make more than one host, but I think it's not possible. Okay. So a composite. When we said composite, it's mean يعني mixture of materials. Okay. A mixture of more than one material. A composite magnetic circuit of varying cross section is shown in figure number 2. So, and the pH characteristic, which is the magnetizing curve, is given in the right side. Okay, so here this example is a complicated a bit. We can see here that we don't have the same cross section. For example, this piece here, L2, has a different cross section from this piece and this piece. Those pieces are identical, L1, L1, and this piece has a different cross section, and also we have an air gap. Okay, so with n is 100 turns, L1 equals to L2, which is 40 centimeter, and A2 equals to, here there is a mistake. Okay, A2 equals to 4, A1 equals to, I think there is a mistake, I'm not sure. Okay, I will check it. Because I thought that we had a mistake. Yes. Okay. We have a small mistake here, but I'm going to fix it. So here A2 equals to 4, A1 equals to 4 A2. It's not 2 A2. Okay, it's 4 A2. So I was talking about this. A1 equals to 4A2. It's not 2A2. Okay. Your classmate is waiting. Okay. I will accept that. Okay. Okay. So here L1 equals to L2 equal to 40 centimeter, and A1 equals to 4A2, which is equal to 10 centimeter, and LG, which is the length of the air gap, is 2 millimeter, and the leakage flux phi equals to 0.0 milliweber. So here you can see that the leakage flux is given. Okay, so it's not neglected. Calculate the required current to establish an air gap flux density B equals to 0.6. Okay. So calculate the current that's required to establish an air gap flux density, or in another meaning, find the current required to achieve 0.6 Tesla in the air gap. Okay, so let's start the solution. Of course, in like the previous one, if you want to find the current, of course we're gonna use Ampere's law. Okay. 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 So firstly, we need to find the in order to determine the current. Firstly, we need to find the total MMF, because the current depends on Ampere's law. We know that F equals to Ni, so the current I equals to F over N. And here we need to determine the total MMF in order to determine the required current enough or sufficient to achieve this current in the air gap. So in order to determine the total MMF, of course, F is equals to H times L. And if we have different materials or different pieces like here, because they are not the same, we have, for example, the air gap, Hg times Lg, and we have the length, the first length, which is H1 times L1, and we have the second length, which is H2 times L2. Sorry, we have two H1, L1. We have two. Okay. Let's see. So since we have different pieces in this core, so each one has a different field intensity and different flux density. Let's see the presentation again. Okay. So firstly, we need to determine the field intensity of the air gap. Of course, here we need to achieve this 0.6. We are looking for it in the air gap. So the required H to achieve B equals to 0.6, H equal to Bg over mu 0, because it's an air gap, so it's equal to 4.78 ampere tour per meter, which is the unit of the flux, the field intensity. So this is concerning the air gap, the first one. Then, so the MMF of the air gap. So here we are looking for the total MMF. We have to find the MMF of each piece of this magnetic circuit. We have L2 and L1 and the air gap. We have three different parts. We need to find the MMF of each part. So the first MMF of the air gap equals to Hg, which is the field intensity of the air gap, times the length of this air gap. Hg can be found from Bg, which is the required field density, and Lg, of course, the length is given. So according to this expression, the MMF can be found from this expression Hg times Lg, and it's equal to 956 ampere joule. Also, Bg equals to BL1. Why? Let's go back to the magnetic circuit. Look at here. Look at this picture here. So here, the field intensity here and the field intensity here, it's the same.
No.
Because they have the same cross section. Okay, here B, it's the same because they have the same cross section. Here B is different in L2. Here B is different because the cross section is different. The flux is the same. It's as a series circuit, as we said before. The flux is the same. It's the same flux that plus the leakage flux. In this case, we have a leakage flux, of course, but the flux in the core is the same in all pieces. But the field density, it's not the same. Here, Lg, L1 here or here, it's the same because they have the same cross section, A1. And in this piece, you see here, in this piece, the flux density is different. Okay? So firstly, we have found the field intensity and the MMF of the air gap. Now, we know that the density in the air gap equals to BL1, which is equal to 0.6. Now, from BH characteristic, as we have done in the first exercise, from the BH characteristic, we are looking for the flux, the field intensity, corresponding to this value of 0.6 Tesla. It's okay, sir, no problem. Okay. No, the leakage flux, it's another issue. I will explain. Does not ماشي معناتها because we have a different change in the cross section that we have the leakage flux. No, the difference of cross section will cause a difference. Sorry, the difference in the cross, the difference in cross sections will cause a difference in flux densities. Okay, but here the leakage flux always there is a leakage flux, but sometimes we neglect it. But sometimes.
So.
Yeah.
What about when we have a gap? When we have the fringing flux, do we have like the same flux and the change will be only for the flux density?
When we have air gap?
Yes, like we have a gap with the fringing flux.
I haven't seen this case fringing.
I think there is a case in the recitation. I think it's the last exercise.
Maybe. We will see it.
Okay, thank you, sir.
Okay. Okay, let's continue. Can you repeat the last point, please? The internet. Okay. I'm seeing that you are connect and disconnect each time. Okay. So I will repeat. Okay. I thought that we can finish 5 exercises in this meeting, but today I don't think so. Okay, no problem. We'll try to finish only this one. I said in this point that the field density here, in the air gap equals to the field, the flux density here equals to the flux density here in the core and the air gap, because they have the same cross section. But here in this piece L2, the field or the flux density is different because we have a different cross section. Now we are looking for, so we have found already the MMF of the air gap, HG times LG. Now we know also that the field density in the air gap and in the core in the piece L1 and L2 is equal. So from the BH characteristic which is given, where we can find H corresponding to 0.6. Okay, so let's see this is the BH characteristic. So this is 0.6, almost here. So H corresponding to 0.6 is 100 in this red cross. Okay. So the value of the field intensity corresponding to B equals to 0.6. Okay. So let's find now the MMF of this piece L1. So since we have found H, which is the field intensity from the graph or from the characteristic BH, FL1 equals to HL1 times the length of L1. Let's go back to the shape here. L1 equals to L2, of course, and equals to 40 centimeter. So we have two pieces, this one and this one, in the right and the left side. So here the field intensity, the MMF, sorry, equals to 100 times 2, 0.4, and equals to 80 ampere joule. Now the flux in the air gap can be found from the density, the flux density of the air gap times the cross section, of course. This is phi g, which is the flux of the air gap. Now the total flux, this is the important remark. The total flux produced by the coil is the sum of the air gap, which is this, because the fringen is neglected, we have only the leakage, the sum of the air gap, which is the linkage flux, and the leakage flux. So here, this one is the produced flux, the total produced flux by the coil. The produced flux by the coil. I didn't set in the core. So the flux produced by the coil is phi c, which is equal to the flux of the air gap, which is the same as the flux in the core. Okay, core. Let's write core here. Okay. So phi g, which is the flux in the air gap, is equal. It's the same as the flux in the core plus the leakage flux. So phi g, or the flux of the air gap, or the flux of the core, is the flux stayed inside the iron core. Okay. And this one, which is the leakage flux, that flux has been floated or disappeared or lost in the air. Okay, let's go back to the shape to explain it more. Okay, to see where is the leakage flux. Okay, so this is the coil. This one is the coil. This one is the coil. Let's change the color. So the linkage flux is the flux here. This is the linkage flux. Okay, so it's the same as the core as the air gap. So those are the linkage flux the leakage flux lines. The leakage flux is here. Okay. Why there is a leakage flux? Of course, the magnetic field is created inside, but sometimes there is, for example, تكون void between the core and the coil, something like this. It's not being concentrated a lot. It's not concentrated a lot around the core. There is a void. We will have a leakage flux. Okay. So it has a small amount. So the leakage flux. Okay. Yes, it's the same. The flux in L2, it's the same as in L1, but the density is different. Okay. The density is different, the cross section is different, but the flux, it's the same. Okay. So the leakage flux can be.
Wait, sir, I didn't understand the last point. In L2, don't we have like the 5 plus phi 1?
Okay, I will get back to it. Okay.
Sorry, thank you.
Okay. So we said that the total flux produced by the coil is the sum of the air gap plus the leakage flux. Okay. Now here the density in we are talking about this point in L2.
Yes, in L2.
Okay. So the flux density in the portion L2 equals to. Okay. So here yes.
The flux is not. It's not the same as in L1. Here we have phi core, and in L1 we will have phi g.
Yes, phi g equals to phi L1. They have the same cross section.
Yes, and for L2 we have phi c.
Phi c, which is the total flux.
Yes. Okay. Thank you, sir.
Yes, here the total flux, because it's you can see that the coil is around. Okay. Why here we are using the total flux? Normally it's the linkage. Here normally it's the linkage flux, because normally it's the linkage flux. Okay, let's see. Yes, we have a leakage in. You are right. Yeah, normally it's the linkage flux, not the phi c. Phi c is the total flux. Okay. We have the leakage flux in phi c. We don't have it in, yes. The flux in L1 it's after, يعني بعد ما مشى الفلكس, after the leakage flux has been taken already. Okay, let's see here. Okay, sorry. So here it should be okay, we are looking for the current. Okay, manage. Okay. So here I think it should be the leakage flux, not the linkage flux. Okay, not the total flux. It should be, but here why it's the okay, let's see. I'm thinking about it. Okay, because here in the second part, in L2 they considered already the leakage flux. Maybe because the flux has been created in this piece L2. In L1 and in the air gap, the leakage flux is not considered because the leakage flux has been lost already. But in L2, I think that the leakage flux is considered because the flux created here in L2 is the total flux. Why? Because the coil is around L2. Maybe before the leakage had happened. I will check this point. Okay. Why in this part they considered the leakage flux? Yeah. But in LG and in L1 and the leakage flux is not considered. Is not considered. Okay. Here. So let's go back to the solution. So the flux density B2 is equals to the total flux. Here I'm not sure, but maybe they consider the leakage flux because the flux is already, the total flux has been created in this part. Okay. And there is no big difference. It's 0.6 and 0.61, 10 to the power minus 3. Here the cross section is different. And B2 equals to 1.22 Tesla. Here, let's go back to the BH characteristic. So the value of H corresponding to 1.22 Tesla is almost 400. It's about 400 Ampere per meter. So it's exactly 410. And here the MMF in L2 equal, or sorry, I have written L1. It's L2. L2 equals to is equal to 410 times HL. L is the length of L2, and it's equal to 41 Ampere joule. Now the current, the total required MMF is FG plus FL1 plus FL2. So we have more than one MMF because those pieces are not identical. Each part we have an air gap, and we have two pieces with the same dimension, and we have another piece with a different dimension. Concerning the L2, I will check why they considered the leakage flux. Maybe because the flux has been created in such part. That's why they take the total flux instead of the linkage flux. Okay, so this is the total MMF. After finding the total MMF, we can find, of course, the current, which is F over N. L 0.1, it's given in the data, I guess. We said L. I didn't mention it, but L. Okay, sorry. L1 it's for L2. Okay, L1 it's for L2. Okay, I will correct it. So L1 is for L2. So here the total current is equal to F over N, the total MMF over N, which is equal to 1077 over 100. And the current here required to create 0.6 Tesla in the air gap is 10.77 ampere. I think I'm going to stop here. Okay, I was expecting to finish the third exercise